how to record. Okay, and we said for the nowadays there's more and more terminals is connected to the network. So for the IPv4, maybe it is not enough for those network for those requirements, and here comes another type of technology, SRv6, segment routing IPv6. So for the to compare with SR-MPLS, SRv6 besides simplify the control plane, the SRv6 also simplify the data plane, the forwarding plane. So it will be much easier to use in the like large scale network. Okay, so in this slide, in this document, we will describe the concept and the fundamentals of SRv6 and its like application scenario, like how to do the configuration for SRv6. Okay, on completion of this course, you will be able to describe the background of SRv6, technical advantage of SRv6, and the basic concept, fundamental of SRv6, and you also will know like how to do the configuration. I mean, physical, static configuration for SRv6 BE and SRv6 policy. About what is BE, what is policy? Actually, yesterday we mentioned about the MPLS. We already talked the concept, but here we will speak this again. And last, we will know how to deploy the SRv6 using the iMaster NCE IP, this controller. But for this part, we just briefly introduced. We will not talk too much about iMaster NCE IP. Okay. Anyway, we have 5 sections for this slide: overview, fundamental, high reliability, configuration, and use iMaster NCE IP to deploy the SRv6. Okay, let's look at the overview first. We know in the very old time for the WAN network, basically we will use the MPLS or maybe IP network. But the IP network, well, since it cannot, for the IP network, purely IP network, since it cannot divide the traffic, to isolate the traffic from different tenants, the IP network cannot do it. And also for IP network, it will be very difficult to do the traffic engineering. So here then comes the MPLS. Okay, so MPLS we have like everyone is very familiar. We can use LDP to create an MPLS based on IGP. We can use MPLS-T to do the traffic engineering. But yesterday we said there will be some issues for MPLS, LDP, and ISVP-TE. So the issues I briefly talked because yesterday we talked a lot about these issues. So basically, LDP first, they based on IGP, so cannot control the path. Second, there will got LDP IGP synchronization problem that if you do not enable synchronization in some under certain circumstance that you may facing packet lost, packet loss, especially during when the main path is recovered and the backup traffic switch back to the main path, you were facing packet lost. And for SVPT, there's another typical protocol to establish the MPLS LSP. The SVPT, first the configuration is very complex and it cannot do the load balancing. For single ISP tunnel, you can load balancing between 2 ISVP MPLS-T tunnel, but with a single tunnel, you cannot do the load balancing. It's another problem for ISVPT. And the third, for ISVPT, they cannot do the calculation in the globally because for ISVPT, each device is calculated their own path. Right. So, which means that maybe for device itself, it thinking this is the best path, but if you look globally, it may not. It may not. So this is the issues for MPLS, LDP, and ISBPT. And then came the segment routing technology. Okay, so the segment routing routing technology, which can like solve the problem which IP, LDP, and ISBPT have. So basically, we have two type of segment routing technology solutions, SRMPS and SRv6. So if you look looking this way, if you compare the classic MPLS, SRMPS, and SRv6, you will find out for the SRMPS, as we said, it simplifies the control layer, simplifies the control plane, because for the SR, the control plane will be put into the controller level, into the controller. So controller will help the SR to calculate the path. And compare the SRMPS with SRv6, we will find the data plane, the forwarding plane also is being simplified. So how to simplify it? How is SRv6 simplify the forwarding plane? What is the good side about it? Let's look the next slide, next page. Okay. SRv6 simplifies the existing network protocol and the network management. In addition, SRv6 supports, very important, native IPv6 and provides the network programming capability, making SRv6 more advantageous. So first, the native IPv6, the SRv6 support native IPv6. This is a very important concept. So thanks to the native IPv6 attribute, SRv6 actually can directly forward it based on the IPv6 routing table. You do not need to do any special configuration. Okay, but how is SRv6 can do that? In the following pages, we will talk about it. And also, we know IPv6 address is a long address. It got like 128 bits long address, which means we can divide this IPv6 address into different parts. We can define different parts, the meaning of a different part, which make the network programming much more easily. I mean, for the SRMPS, they also have the capability for the programming, right? We can arrange the sequence of the segment list. Then we can program in the path. But for the SRv6, since we can divide it, IPv6 into IPv6 address into many different areas, so it makes the programming much more capable compared to SRv6. SRMPS. Okay, so let's directly look at the SRv6 fundamental. Okay, let's have some basic idea. First, how is SRv6 help us to do the forwarding? This is the first difference, a big difference compared to the SRMPS. For SRMPS, we know that we have a, what do we call it, a segment list, right? We have a MPS label, looks like a stack, like 1000, 1001, 1002, 1003, 1004. And each devices, when it receives the SRMPS packet, they will pop out the outer label, right? This is then forwarding to the next devices. This is SRMPS do. This is SRMPS forwarding behavior. But for the SRv6, it is different. First, SRv6 SRv6 using a header called the segment routing header, or we can call it SRH. Okay, we also can call it SRH. SRH looks like this. It is still a list. It is still a segment list, like B, C, D. But when I do the forwarding, for example, from this ingress to B, so I will use this B as a destination. And when it reach to B, then header will move to C, and it will give to C, and then when the C receive it, it will move. The next stop will move to D, move to here. So the whole path from ingress to egress, for the whole path, the SRH, the length of SRH will not change for most of the time. Most of the time, it will not change. And so they will just changing the you can say change the indicator from here to here, change the indicator and guide the traffic to do the forwarding. So in this way, SRH will SRv6 will very easy to do the reverse trace. It will know that these devices came from which, this packet came from which path. Okay, for the segment, for the SRMPS, since for SRMPS, for each time when it reaches to a certain point, they will pop out the outlabel. So for the SRMPS, they cannot trace back like where this traffic came from, where this traffic came from, how many hops, which hops they are passing this traffic. But for SRv6, they can do it. I guess it is very clear. Okay, so what is SRH really looks like? It looks like this. First, the SRH, of course, it is behind IPv6 header. It will be encapsulated behind IPv6 header, and for this is IPv6 header. So the next protocol is 43. Protocol ID 43. The next header is 43. And it indicates this is SRH. And this is IPv6 SRH header, and you can see inside it, because next header, this is for the like what is below here. Maybe there's another extension IPv6 header. So this is next header. Length, we just passed. And the root type is 4. This is fixed. 4. If it is 4, it indicates this is SRH, the segment routing header. Okay, the very important thing is here, the segment left. The segment left is a number, it's an indicator. For example, if segment left is 2, which means now the destination IP address is this. If segment left is 1, which means this destination is, this packet destination is going to here. Okay. So this segment left can active the segment. And this part, this is the segment list. Segment ID list. So it will describe the path for the certain traffic for certain packet. Okay. And so for this SRH, we know this is indicate the path, right? So for each of this field, we call this field the segment ID or SRv6 segment. Okay, there's a lot of noise. Wait a moment. Wait a moment. Wait a moment. Let me. Okay, so is this better? Because some students thinking my microphone is a little bit have a lot of noise. Is this better? The same? Wait a moment. Wait a moment. Let's see. Maybe microphone. A lot of noise. Is this better? Okay. I don't know. Maybe there's some noise. But anyway, okay, let's continue. Okay. Oh, where is it? Okay, we talk about segment now. So for SRv6, the segment length is 128 bits. Just have the same length of the IPv6 address. Okay. And so this segment, this SRv6 segment, can divide it into 3 parts, which is a locator, function, and argument. You can say locator, function, and argument. Arguments. The locator will identify the location of the network node, which means for each network node, this locator, this part, must be different, must be unique. Okay, because this is a identifier. This is ID for the devices. Okay. So this is a little bit example like how you configure the locator. You can say this locator, this is a locator and the length for this locator. Okay. So this locator, after you finish the configuration, you should use like the IGP or BGP to advise this locator. But about this, we will mention a little bit later. But anyway, this locator, the purpose, meaning for this locator, the purpose for this locator just identify the network device. And second is function. Function also we can call it OP code, operation code. So this function means what is this segment ID used for? Either we can use this function, we can use the locator is being fixed, and if the opcode ID is ::1, so which means the segment SRv6 segment is 2001:DBH :ABCD ::1. Okay, so this means I am located here. This is my locator. I am located here, and this ::1, this segment will be used as an NX segment. So what is NX segment? Later I will mention, but basically NX will means the interface. Okay, so this segment means certain interface. It indicates some certain interface. If I receive the destination is for this IPv6 address, I should send out from this interface. Okay, and here's a lot of function which will be defined by the RFC. We will mention some commonly used functions. Okay, and this is a function. Okay, and the second is argument. Arguments normally it is an optional field that you can configure it or not. So argument it will, how do I say, define some additional information for this segment. Like if you want to configure, you can. But most of the time, if you do not have some special requirement, you can just leave it behind, leave it to empty. Okay, so for SRv6 segment, we have many types. This just some commonly used segment types, but we have many others. Let's look at those very commonly used segments. First is end. The end indicator the endpoint seed. This endpoint seed you can consider will be same with the node seed. In the SR MPLS, we know that the node seed will indicate the device itself. So in SRv6, the end type segment will be the end seed, will be the node seed, have same concept. So this end seed indicator this devices itself. The NX will be indicator the layer 3 interface, the layer 3 link which connected to another device. So if I want to use a segment to describe this interface, I will use NX type segment. And also we have this DT4, DT6. This DT4 and the DT6 indicator the VPN. Those kind of segments have the same meaning of the private label. I think you guys all understand about the MPLS VPN, right? For MPLS, we have dual label, right? We have outer label and inner label. Inner label will be the private label, right? So for the end DT4 or end DT6, their function will be same with the private label. It will indicate this traffic is belong to which VPN instance. Okay. And besides that, we have another is DX4 and DX6. This DX4 and DX6 indicator I should send out from which interface. So X will stand for like interface, right? I should send out from which interface. So the difference between NX and the DTX, this difference is for the DT4, DT6, this most of the time will be at the PE. If I want to send into the CE, I will use the DX4, DX6 to indicate I should send into which CE. And X without a D. D means decapsulation. Okay, so anyway, the NX means I should forward to which P devices or which PE devices. But for the DX4 and the DX6, it means I should send into certain CE. So it is different. Okay. Now let's continue. So when you look at this type, segment type, you may be wondering like, what is this X, T, D something means? They actually, those letters is being defined. Okay, so the X, the NX, the DX, this X stands for I should forward the packet through one or a group of layer 3 interface. So for example, NX means I should forward from which certain layer 3 interface. I should from this layer 3 interface and send out. So you're going to say X stand for this. T will stand for to specify the routing table and forwarding the packet. For example, I want to checking some certain VPN routing table and do the forwarding. So here you can say DT4. The T means this packet, when I receive this packet, this DT4 type segment, I should check in certain VPN routing table and do the forwarding. And the D means decapsulate. Decapsulate the packet. For example, this DT4, DT6, most of the time it will be the PE and the CE. It will DT4 and DT6 means if I want to send out, this segment will be the DT4 DTX, DT6 DX, 4 DX6 segment, and with the D, I should decapsulate, remove, pop the SRh and forwarding to CE with the native IPv6 packet. So this is D mean. And we also have something else like V. This is for the virtual. I should specify a routing table, and based on the VLAN information to do the forwarding. This is for layer 2 VPN. U is also same. This is for layer 2 VPN. M is for layer 2 multicast also. And we also have something like B6 and BM. B6 will be used to do the stitching labor. I hope you still remember the binding labor, stitching labor. And BM will be used to let the SRv6 can communicate with SR-MPLS. Sometimes we will use BM. But about the BM, VUM, those 4 types, we will not mention too much in this course. Okay. So here is some example. Here is some example. For example, P1, I will use the end seed to indicate this is a P1, like here. And the NX will be indicated to this interface, like 12. Okay, you can see here is another. And for the PCE, maybe it belongs to certain VPN, for example, VPN1. So in the P1, for VPN1, I will use this seed to indicate the VPN1. Okay, to guide to let the device know if I receive this packet, I should send it to which VPN. And if you look closely for this different type of seed, you will find out that at this part is all same. So this part is locator. It is a locator. Okay, so you can see for each devices, they share the same locator but with different function. Okay, some number that will be used as an NX, some number will be used as an NC. Okay, and for each locator, it is this is unique. It is different for each devices. So, okay, and let's continue. And for the SRv6, the end X, the end DT2, DT4, DT6, those kind of devices, when this segment, when they do the forwarding, they have something called a flavor to do how does this, to do a little bit behavior like PSP. This is remove the SRh on the penultimate endpoint node. USP removes SRh on the ultimate endpoint node. USD decapsulates the root IPv6 header on the ultimate endpoint node. Okay, so about this flavor, later when we talk about the SRv6 forwarding, you will see this again. Okay, and here's a little bit of configuration, like this is how you configure the SRv6 locator. So you go into the segment IPv6 and create a locator. It will be okay. And this is how you do the configuration for special function. So you set some number, and this number will be function as an end segment. and some other node, some other number you function as an x, and you can follow it with flavor, either PSP or maybe PSP, USP, USD, based on your requirement. And here is some example, like this is a locator example. Okay, so this is a basic idea for SRH. Any question? Okay, so let's continue. So just with the SRH, just with the header, how to do the forwarding? Just with header, how to do the forwarding? Okay, so if we wanted to forward the SRv6 packet, first we need to get the idea of SRv6 node. So for the SRv6 system, for this solution, we have three types of node. First is a source node, which means the source, the terminal source, the SRv6 terminal source. Okay, source node, I guess it will be very easy to understand. Another is a transit node. The transit node means I will not be participate. We will not be a part of SRv6. I only do the forwarding. For example, I only do the forwarding the SRv6 packet, but do not perform the SRv6 processing. I will not changing any information for SRv6. I only based on the destination IPv6 address to forwarding to the next end node. That's all. This is transit node. So this transit node can support the SRv6, or it can be just native IPv6 devices. Both is okay. Either you might support the segment, or maybe you just support the IPv6. It doesn't matter. They all can be worked as a transit node. And the last is endpoint node. So first, endpoint node is not mean the endpoint of the SR kernel, SRv6 kernel. It does not mean that. It is only means that this node will receive and process SRv6 packet. Okay, in which the destination IPv6 address is a local seed or local interface address of the node. So let's look at the one by one. What is a source node? What is a source node? What is a different type of node? What is those type of node do? Okay, for the source node, this is where they add the SRH header into the native IPv6 packet. Sorry, it's the SRv6 actually can carry the IPv4 packet, so I should not say this. But this source node is where you add the SRH header, where you added the SRH header. So you can say here R1, let's assume the R1, the forwarding path is from here to here to here. So since R1 is a source node, when the traffic came into the R1, R1 will give this packet SRH header. It looks like this. The SRH segment left is 2. I mean, this is 2, 210. Okay. So the 2 will be F03, F03 colon colon 3, which means this device. It's an AND seed, right? It's an AND seed. So the R1 will send out based on the IPv6 routing table. It will send out. It will find out how to go into here. So the device is so in the source node. When you add the SRH header, there will be two ways. First, we call it insert. Another called incaps. The insert means I will insert the SRH behind the original IPv6 header. The incaps means I will put the IPv6 and a new IPv6 header and the SRH above the original packet. this packet can be IPv6 or can be IPv4. But I will encaps external header above your original. So the insert, you can only use IPv6 header, but if we use encaps way to add the header, this can be IPv6 or can be IPv4 packet. Okay, and here we can say for the insert and encaps, I guess it will be very simple. And encaps dot layer 2 means I will add the IPv6 header before the layer 2 header, like MAC header or PPP header before that. This is for the encaps layer 2. And we also have something special that h.insert.read. This read stands for reduce. Reduce. What does this reduce mean? It means for the first header, like for the source node, there will be two ways to do the encapsulation. They can have FC0, FC01, ::1. Without the IED, without the reduced, it means when the R1 encapsulate the SRh header, R1 will thinking the first hop is itself. So it will add the FC01, ::1 into the SRh. With the reduced, with this feature, it means the R1 will not thinking itself as a first hop. So it will not encapsulate the FC01, ::1 into the header. Okay, it is different. So this is a source node behavior. And let's look at the transit node. The transit node, as we said before, they do not have the capability to process the SRv6 packet. What this segment can do is just help us to forward from one node to another endpoint node. So you can say when R1 forwarding to the R3, R2 only help us to do the forward out and will not changing any information inside the SRh. And the last type of node is endpoint node. So the endpoint node will be the node which can processing the SRv6 header. So for example, the R1 knows the next hop will be the FC003, ::3. So it will sending to R3. R3 will be an endpoint node. And when this endpoint node is receives the packet, they will move the indicator to the left. First it is here, then it is here. And R3, when it send out, it was sending to the 04, ::4, and the SRh is become this. And the last segment, this one, what is this used for? And we can see this is a DT4. So this indicator the VPN, which VPN this CE2 belongs. Okay, so this is endpoint node. Any question for those three type of node? Okay, so let's continue. So for the SRv6, how to do the forwarding? So there will be two forwarding mode for the SRv6. First, we can use SRv6 policy. For SRv6 policy, we can manipulate the forwarding path. We can plan the forwarding path. This is for SRv6. And another is SRv6BE. It is a simplified implementation of SRv6. It can only provide the best effort forwarding and does not involve SRH. For SRv6BE, they do not have SRH header. It's just like the LDP, this one. Okay, so how to do the forward? Let's take an example here. Let's assume there will be the network. It looks like this: R1, R2, R3, R4, and each of them have locator and have the end seed. And this locator will be advised by the extended OSPF or RSS. So it will exchange with each other. So how about R2? So for R2, this will be used as a transit node. So in R2, I do not let this locator being advised to other devices. So anyway, R1, R2, R3, R4, based on the RSS, they will all know each other's locator information, and this information will become a routing table. For example, in R1, it knows FC01::, it is a local. And for 03::3, the next hop will be R2. The rest of the thing is same. You can see it is all same. It will create an IP routing table. So the the SRv6 packet will forwarding based on those routing tables. Now, based on that routing table, let's look at how is SRv6B and T do the forwarding. For B, it will be very simple. Let's assume that from R1, I want sending a packet to R5. So I just put a destination IPv6 address is FC01::1:5. This is it. I use this as a destination and use this as a source. And it was sending to the router, and the router based on this routing table, it was sending to its destination. Okay, so this is for SRv6BE. It just looks like a normal IPv6 packet, right? Now let's look at the SRv6 policy, because before we already mentioned about what is the concept of policy. We talk about SR MPLS policy. We already mentioned the concept of policy. So here we directly look at what is forwarding in SRv6 policy mode. Okay. So for the SRv6 policy mode, it has the SRH header, right? It has the SRH header, and the SRH header, there will be a segment list. This is a number 2, number 1, number 0. 2, 1, 0. So when R1 sending out, it was one sending in here to here to here, one sending in this way. So the first segment, the bottom segment, will be FC03::3. And meanwhile, this IP address will be, this segment will be put into the destination IPv6 address. And R1, based on this destination address, will do the forwarding. It will send into R2. R2, based on its routing table, based on this routing table, it will send into R3. And since R2 is a transit node, it will not processing the SRH header. It will just leave like this and send into R3. And R3 it finds out the destination IPv6 address is R3 itself. So, and it reads the header for the IPv6. It finds out this is the SRh header. So the R3 will change the indicator from here to here. FC04::4, and also put this segment into the destination IPv6 address. Then sending to the next devices. Next devices basically will do the same thing, right? It will do the same thing. And when R4 wants sending the packet to R5, there will be some behavior called the PSP, penultimate segment pop, PSP. So if the SL equals to 0, and when it send out, they can enable, they will do the PSP behavior to pop out the SRh header and send into its destination. So this is a forwarding in SRv6 policy mode. Any question? Beware that this South IPv6 address is not changed. It will not change, but the destination will change based on when the traffic reach to each endpoint node, it will change. Okay. Okay, now let's continue. That is a basic concept of SRv6. Now about the SRv6 BE, it is very simple. When we talk about typical SRv6 application, we will mention. But now let's look at the SRv6 policy first. How is SRv6 policy establish the path, and how did they do the traffic steering? Okay, so what is the policy? The policy is a new traffic steering technology developed based on the SRv6. And the SRv6 policy is a set of candidate paths consist of one or more segment list, which means in one SRv6 policy, we can have multiple paths. So for each seed indicates the end-to-end path. Okay. So if the packet is steered into a SRv6 policy, the head end will add the seed list into the packet, and other devices receiving the packet execute the instruction encapsulated into the list. So let's look at the SRv6 policy, the detail for SRv6 policy. First, if we want to use the SRv6 policy, we need to identify it. How to identify this is one policy. So same with MPS policy, SRv6 policy also identified by the tuple, head end, color, and endpoint. Here is something I want to make it clear first, is endpoint and endpoint node is different. Endpoint and endpoint node is different. This is a type of device, and this endpoint means the end of the tunnel. End-to-end tunnel, another end of the tunnel. Okay. Maybe for each of these devices, it is an endpoint node. It is endpoint node, but endpoint is here from south to the destination. Okay. So for each with the same south, same destination, and with a certain color, we will define one SRv6 policy. For example, here, the SRv6 policy. color is 15, and maybe there's a 20 policy 2, color is 20 from here, endpoint is here, and the color is 20. And beware that we can have multiple paths, and we can have active and backup paths for certain policy. And SRv6 policy, SRv3 policy, same. Source, endpoint, head end, endpoint, and the color. So this is how you define the policy, how you define the kernel. Okay. Now let's continue. So for the SRMP policy, we have different path model. We have some path model. So first, let's look at how it's a policy path to establishment. First, we know SR policy, we can, for the same head end, same endpoint, same color, we can set one primary path, one backup path. And for the primary path and backup path, you can have multiple forwarding paths. You can have multiple ways. You can have multiple segment lists like this. So you will choose one candidate path, and inside this candidate path, you can do the load balancing based on the weight. So how to establish the SRv6 policy path? Basically, you will have two ways. First, you can use IMUST-NCE, and second, you can use manually deployed. If you want to use IMUST-NCE to deploy the SRv6 policy, you need the BGP-LS to report your protocol. No, sorry, not protocol, topology, running state essential, and you need to use SR policy to tell the head end, tell the source what is the path, what is the forwarding path for this tunnel. And the third is a netconf. Netconf will be used to deliver some special configuration like load policy, like the VPN configuration, etc. Okay. And so for BGP-LS, it will help us to help the NCE IP to collect the information. So which kind of information they have, which kind of information to collect. So topology, prefix, SRv6, locator, seed information collected by the ISS OSPF. You can see this is topology node information. This is like node. This is myself. This is myself, and this is topology link information. Local IGP router. This router remote IGP router. So you can see this is this devices is connected to this devices. So this is topology link information. We also have SRv6 information like seed, like locator. Locator, I do not put it here, I guess. Locator, the seed, you can see it in the BGP-LS. Also, we're going to say like SRv6 policy state, the kernel state, whether this policy is up or not. This will also be collected by the BGP-LS, this state. And once we tell the NCE, the network situation by BGP-LS, the NCE IP will sending the SR policy using the BGP IPv6 SR policy neighbor. It will send to the head end. For example, my path is P1RR, PE, P4, like this, forwarding path like this. So the NCE will send the SH, the segment list, to the P1. So this 5.1 is the first, then 6.1. Then out interface here. Okay, it will creating this traffic path. It will create this segment list. So you can see this is the SR policy. It's sent down to the devices. It looks like this. It's just a routing table, to be honest. It's just a routing table. So you can see this is a segment list, and we also have something special called binding seed. This is for the stitching. If you want to stick together two paths, stick them together, we can use the binding seed. About this binding seed, we will mention a little bit later about the stitching. So after the SR neighbor forwarding the SR policy segment list to the head end, you already established the SRv6 policy path. This is for inside of the AS. So between the AS, we will also use the BGP EPE technology, as we mentioned yesterday, EPE. So EPE, they basically will give the peer, they will assign the end X to the BGP peer. For example, this router and this router, they created two neighbor. So for this neighbor relationship, they assign those segment seed, and for another device, it's same. So it depends on, based on the BGP neighbor, it will assign the SRv6 segment to the peer. So you can say, if I want to do the forwarding, going to the FC00, FC02, 2, then send out from this interface, 1C, send out. You can say 1C, send out, and reach to the another end, FC03, 3, here. Then it's sent out with FC04, 4, and we're sending to its destination. Right? Okay. Any question you can write down in the chat. Okay, so let's continue. Now let's talk a little bit of patch stitching. That especially during the inter-AS forwarding, forwarding between the AS, between different AS. Sometimes we will use the path stitching. As we said before, that devices have some limitation for the segment stack. That the segment stack length cannot be cannot put a very deep segment stack, because the devices cannot understand all of them. So let's assume that those devices, they have some limitation for how many stacks they can read. Let's take an example is 4. 4 stack X is the maximum. 4 segment list is a maximum stack depths. 1, 2, 3, 0, 1, 2, 3, so 4. So if we do the forwarding just the 4, we cannot reach to the other end. So what to do? We can do a stitching. Let's put the this FC03, 100 will be used as a binding seed, the stitching seed. So when the C1 wants to send in the packet to C2, C1 sending packet to P1, P1 will give this traffic SRH header FC02, 2. So it will send into these devices first. And this device is based on the BGP EP. It was sending out from this neighbor, sending to its own neighbor. And then here comes the stitching seed. FC03::3. Then it will put another SIH header before it. The FC03::100 means the path. This path means from SBR2 to PE2. So it will be FC04::4. But if you got another devices, they will put the whole information for the path. Okay, for example, there's another FC05::5. So here we'll add another is FC5::5. Okay, so anyway, when the ASBR receives this packet, they will based on the FC04::4 sending to its destination FC04::4. When the P1 receive it, P2 receive it, it will remove the out header because the SL is 0. It will remove the out header, and it will checking the inner header is FC04::100, which means this certain VPN. So this stitching, this mode is what we call the insert mode. It means I will insert a new SRH behind the old IPv6 header. And another is in-caps mode for the stitching, is they put a new IPv6 header and a new SRH above the old IPv6 header. So the function of those two is pretty much same. Just to realize these two, to realize the function, the way is different. The in-caps mode and the insert mode. Insert mode directly inserted as the SRH behind the old IPv6 header, but for the in-caps mode, they will put some new IPv6 header and a new SRH header. Okay. So this is how you establish the SRv6 policy path. Any question for that? Okay, so let's continue. Let's talk about the traffic steering to the SRv6 policy. How to lead the traffic into the kernel, into the SRv6 policy. Okay, we know for SRv6 policy, we are using the source, the head end, endpoint, and the color to identify the traffic, to identify the tunnel, sorry. So for example, the CE11 sending a packet to the network 1 or network 2. So network 1 and network 2, they have the same head endpoint, same head end. So as long as I can define the color, the different traffic will go into different kernel. So how to do it? Very simple. Let's look at how did they forwarding the root entry, you will know. CE2 sending to the PE2, sending to this normal root. And when the P2 based on the VPN v4, VPN v6, eVPN routing, eVPN IP address family, they will sending to its peer P1. So during your sending the root entrance, there will be 3 things you can do. First is when the root entrance trying to send to the P1, the P2 can apply some export root policy to add this color. The color looks like a 0 colon something. This is your color number, right? This is a color number. Or maybe when the P1 receives the router, we also can deploy an import root policy. And if you do not configure any policy, when it receive and sending the, while it receive and sending the root entrant, you also can configure the color in the VPN instance, which means all the packet in this VPN instance will go into the same color. So there will be 3 ways to steering the traffic into the SRv6 policy. So let's assume that P1 receive a packet with this color. The color is extend community attributes. So we can see it here. So when the CE1 destination is network 1, it gives to P1. P1 check, okay, going to network 1, next hop is P2, and the color is 15. So the P1 will try to find the tunnel with the color 15, and it will steering the traffic into this color, into this tunnel. So another like destination network 2, the behavior is same. Behavior same. And also, as we said, we can use SRvIF to directly binding the color and help us to do the forwarding. Okay. Continue. And this is a color-based traffic steering to the SRv6 policy. And besides that, we actually have something special called a DSCP-based traffic steering to SRv6 policy. So what is DSCP-based? What is color-based? So for color-based, if you have the same destination with for example, in this network 1, let me directly look at it. For example, in this network 1, I have 2 services, FTP services and HTTP services. They are all in the network 1. And if we use color-based, it means from CE1 to this network, they will always go in the same SRv6 policy. But maybe inside of this network 1, we have different type of services. Different services have different requirements. So what we want to do is, for different DSCP packet, I want going to different kernel. So what to do it, how to do it. So it will be working like this way. First, we need to have something called the mapping policy. The mapping policy means different DSCP value will steering into different SRv6 policy. This is what we call the mapping policy. Okay? And this mapping policy has the color, Okay. So I will, when I'm forwarding the network, when I'm forwarding root entrant, I will also give this root entrant a number, a color number. And this color number will be the mapping policy number. So either you carry this color number in the root entrant, or you can directly configure in the VPN instance, which means all the VPN instance packet in this VPN instance, they were all based on this mapping color, or maybe based on the root entrant. Okay. So when the package do the forwarding, what they will do? First, they will based on this color. Based on this color, they will finding the mapping policy. Then the traffic do the forwarding. While do the forwarding, the devices based on the DSCP value and based on the mapping policy, it will decide. For example, DSCP 24, it should go into the SR policy, this policy. DSCP 28, it should go into this policy. Okay, so here, as we can say DSCP-based traffic steering, we have 2 colors. One color is the indicator which mapping policy the P1 gonna use. And the second color, this is the real path, the path color, the SRv6 policy color. This is a real color which will help us to do the forwarding. And this color is just used to find the mapping policy. Okay? Is this any question for this? No question? Okay. If there's no question, let's continue. So let's look at the typical SRv6 application. So this is level 3 VPN over SRv6 policy. Okay. So first, when the let's assume CE1 wants sending a packet to the CE2 network 2. Okay. So CE2 was sending the route to the PE2. Next hop is CE2 destination network 2, and the PE2 will send into the PE1 and added the color. So this color we need to use the route policy to do it. Okay. Added the color, added the RT, and added with this. What is this? This is NDT4 segment. This function, as we said, is similar with private label. Okay, sending to its destination P1, P1 sending to a CE1. So when CE1 sending a packet to CE2 network 2, we're sending like this way. South CE1 destination network 2, sending to the P1. P1, based on the routing table, based on the color, it will find out I should go to this forwarding to based on this tunnel. So they will add the SRH. The header will be 02 : 2, 03 : 3, and 03 : 300. So this can help us to forwarding to the P1 first. Then P1 receive this. It will processing the SRH header and sending to the FC : 3, which will be these devices. It will send into here. And then PE2, based on this segment. This segment, the PE2, no, this is a DT4 segment. This DT4 stands for certain VPN, for example, VPN 1. This indicator is the VPN 1. Then they will pop out this header, and based on the destination IP address and based on this VPN, it will send out to CE2. Okay, this is one using scenario, and you can see this is IPv6, IPv4 packet. Okay, so for the SRv6 policy, they can carry both IPv4 and IPv6 packet. There's no problem. You can carry that, no problem. Okay. Now let's continue. So another is a layer 3 VPN over SRv6 BE. So BE, since I will be a little bit different, because the BE do not have a, it's not policy. They do not have color, those kind of concept. So what is they gonna do? So the CE2 sending the packet to sending route to PE2. PE2 sending to the P1 and then look at the information which carried in the BGP route. They will carry the private label. They will carry this and the DT4 sending to the destination, and destination sending to CE1. So the CE1, when it is sending the packet, the outside they will encapsulate the destination is look at this. This destination is NDT4. So it was sent. So how to forwarding to the NDT4? Because they are FC003. FC03. This packet, this destination is FC03. It's a locator. We can based on the IP routing table because this locator is being advised by IGP. So everyone know how to get to this locator. So the P1 will based on the IPv6 routing table sending to the P1 and sending to the PE2. And PE2 receive it, the destination is FC03::300. The PE2 know this packet is belong to this certain VPN, let's say VPN 1. And then going to VPN 1 checking how to get to the network 2, and it will send into CE2. So this is layer 3 VPN over SRv6 BE. And also let's look at the native IPv6 over SRv6 policy. They are similar. They're very similar. Okay. For the native IPv6 also can use SRv6 policy to carry the traffic. So basically, the P1 they will also carry the color, but no RT because it's a native IPv6. And the P1 will add the policy SRh. You can see the last hop is this. Last hop is this. So based on the IP routing table, it will send into P1, P1 to send to P2, P2 checking the destination is net2, and SL is 0, it will pop out this SIH and send into the CE2. Then CE2 receive it. This is how you use SRv6 policy to carry the native IPv6 packet. Any question? Any question for SRv6 fundamentals? Okay, no question. Okay, if you guys do no question for the SRv6 fundamental, then maybe let's take a break first. Let's take a 10 minutes break, then we will continue.
SRv还有没有可能还有1-2个，而且他们说他们基本上上不了站的，其实上不了站的，因为有很多能做站是吧？我是觉得这个太对，是机遇的话，我开一般少。今年的香港还有反正今年现在很便宜的吗？因为机有就贵了，就现在真便宜了吗？我好久没摸这些东西了。就几十块钱这样子。一口。以前是一口是贵的这个，你想想现在基于电都已经到家。 哦，对。发封邮件给我。要不要我发？或者是看你发还是发那个中华大中华？哎，可以，或者是发那条线是一定的线。好，麻烦。
Okay, so let's get continue. Now the next, let's talk about the SRv6 high reliability. So for the high SRv6 high reliability, it will be similar to the MPLS reliability. The concepts are pretty much same. A little bit overview. We just know, like in the one barrier network, we need high reliability. We want the forwarding path switching fast. I want them like just immediately switched, can switch maybe under 50 milliseconds. Maybe I want them. Okay, so let's look the overview for mountain layer reliability solution for SRv6. So basically, we can divide our network into 3 layers. First is a physical layer, all kinds of like link devices, etc. Second is tunnel layer. So tunnel layer is like SR tunnel, SRv6 tunnel, tunnel layer. And then the third layer is service layer, which is like the VPN layer that I use L3 VPN or eVPN to forwarding the VPN routes, right? So for each different layer, they have different type of technology to guarantee the reliability. So for the service layer, we use VPN FR. About this concept, we talked yesterday. And for the tunnel layer, most time what we use is FRR. FRR, the TRFA FRR, middle point protection, this kind of thing, or HSB. And for the physical layer, those devices, for devices high reliability, we can like put multiple, like a dual control board, dual FSU, those kind of backup component for the key pump, backup part for the key pump component, and also like the redundancy link, redundancy part. This is for physical layer. And about the physical layer, we will not talk too much. We will focus on the tunnel layer and the services layer. But anyway, if anything, any physical link got problem, IGP got problem, RSP got problem, VPN got problem, we have different type of technology can deal with this situation. And but of course, to deal with this situation, we must have use the BFD to detect there's a problem, right? To solve the problem, we must fastly, rapidly detect the problem. Then we can find some way to solve it, right? So here is a picture. But anyway, you can check it later. I will not talking too much. I will directly jump into the technique. So first, let's look at the usage scenario for reliability technology for mountain layer network. Okay, so let's categorize the services. Basically, we can divide our services into 2 types. One is the common services. Another is high SL requirement services. So for the common services, what we need to do is local protection and end-to-end protection. And for the common services, there will be 2 types of tunnel, BE and SRv6 tunnel. Okay, so for those kind of tunnel, there will be 3 type of failure point. First is from 4 to 8. This is in the middle area. So to detect this kind of fault, we can use BFD for interface. And in this area, anything happens, we can use TRLFA or middle point area TRLFA to to create some bypass tunnel to continue forwarding the packet. So those kind of switchover can be switched in 50 milliseconds. And if the failure point is 309, which is the endpoint, we will use the VPN FR to deal with that. And for this, we can use IPFR or VPN mixed FR to fastly switch over to another path. Okay, this is the common services. And for the high SLA requirement services, we can use, this is the mailing means SRv6. So from 4 to 8, besides the TRLFA, we will deploy the HSB, the standby path, the end-to-end standby path to provide some to guarantee our SLA. So this is also can switch over within 15 milliseconds. And if 9 and 3 and 9 this got a problem, then wait a moment. Then we can use the VPN FR. And for this area and this area, we can use VPN mixed FR and IPFR to do that. So to make this happen, we need to introduce two types of technology. One is for detection and the tunnel protection. So first is tunnel detection technology. So basically we will use two. One is SBFD, another is ping and trace route. So SBFD we actually mentioned yesterday about like what is SBFD. Basically it's similar to the one-armed BFD, which is widely used in the old time. So about this SBFD, I guess let's just pass. There's really not a lot of things need to say, just a normal BFD. So another one is ping and trace route, which also will be widely used during you manage the SRv6 policy. So first, the ping and the trace route, there will be two solutions, like how to do the ping and trace route. The first solution is here, that you put an O bit in the flag, and if with O bit we can directly do the segment by segment test, we can do the ping trace route. Another is we set some special segment seed. We can call it end OP. OP means operation. They can do end-to-end test, right? It is different, segment by segment and end-to-end test. So those two types of solutions have different using scenario. Okay, so then let's let's continue. So for the ping, it will be very how do I say, very simple. Just do the SRv6 ping. We can ping the OP and OP to do the ping, and just sending a packet request and send back. And this is a segment by segment ping, which means we are using this way, using O bit, or we can just directly ping this end-to-end, use end OP seed to do the ping. Okay. And the trace route is similar. This is overlay trace route. So this overlay trace route most of the time is trace route the policy. trace route is SRv6 policy. From head end to the endpoint. Okay, when it reach to the endpoint, and it will reply. Okay, another is the non-overlay trace route test. It will test the one by one. It will test the P1, and then P1 reply. Then test the P from P1 to P2, then reply. This is non-overlay. This is like a hop by hop. So there will be two types of trace route detection. Okay, so this is how you detecting the how you use the BFD and the trace route ping to manage your how do I say your policy. And after you use either BFD or ping trace route, you detect there's a problem, then you must find some way to protect it. So to protect your kernel, the SRv6 kernel, you have two ways. One is local protection, another is end-to-end protection. So for local protection, most of the time we will use the TR-RFA-FR and the middle point TR-RFA-FR. And we also will use a micro loop avoidance. Those concepts is similar with the SR MPS protection. And end-to-end protection, we will use the HSB for the most of the time. But besides that, we can use ECMP or we can use the best effort path to do the end-to-end protection. Okay. So let's look at how we do it. First is the TR-RFA-FR. So about the concept of the TR-RFA-FR, why we need the FR, what is the FR situation, why we need the TR-RFA, this algorithm, we actually already mentioned yesterday. But in a short word is, for TR-RFA, no matter which kind of topology you are facing, you can always use the TR-RFA to finding a bypass tunnel. Look at this. Let's, for example, in this topology, for PE, for the south, the P space is only P1 and P2. For Q space is only P4 and P3, which means P space and Q space, they do not how do I say, overlapped with each other. You cannot find the PQ point. Without the PQ point, the devices were thinking, okay, maybe there will be some potential loop. So I will not forward it. I will not create the path. Okay, so what to do? The TR-RFA working like this way. First, as long as all these devices enable the segment routing function, the SR function, all devices knows the topology and knows each device's segment. No matter you are using the end segment or end X segment, all devices know it. Then they will do the calculation. They will finding the P space and Q space, the nearest devices, one device is at P, one device is at Q. The P space and the Q space, the closest point. During that point, between that 2 points, they will create a tunnel, automatically create a tunnel. So what is this tunnel looks like? Okay, so this tunnel looks like this. For example, P1 is still going to P2. So the P1 sending the device packet to P1. P1 find out this packet got a problem. So I want to go into the backup path. But P2 and P3, they are not overlapped. I mean, one is P space, another is Q space. So I should find some way to send the packet from P2 to P3. How to do it? We can use a tunnel. So the P1, before they send out, they will encapsulate an additional SRh header with FC03C4, which is this interface. So when the P2 receives this packet based on this, P2 know I should send the packet out from this interface to the next device. So the P3 receives this packet, and since P3 is in queue space, in queue space means from this point to the P2 there will be no loop, right? So the devices will send the packet to the P2, sending a packet into the P2. So this is how the TR-RFA-FR works. They just add an additional kernel, the additional header, so we can forcefully forwarding the packet from P2, from P space to Q space. Here we are actually using the kernel. We forcefully forwarding the packet to this Q space. And the Q space reach to the destination, definitely there will be no loop. There will be no loop from Q space to destination. So then P3 will just send in the packet to the P2. So this is how it's done. How this done. So this is TR-RFA-FR. Any question you can ask, by the way. Okay. Okay, so let's continue. But there will be some limitation for TR-RFA-FR. Actually, this we also mentioned yesterday is if there are some paths, I was creating the packet, and in this SRh, we know we have to pass FC03::3. I must reach here, then I can send back. But now the FC03::3, this device got a problem. So how can I give the packet to? I mean, I should sending the packet to the FC3003 first, but this device is filled. I cannot send into it anymore. So even the TR-RFA-FR cannot solve it, because let's look at the TR-RFA-FR, FC04. The next hop is this. So TR-RFA-FR is finding some way to sending to this endpoint node. But if the endpoint node got a problem, I cannot send. Even with TR-RFA-FR, I cannot do it. So here is another protection called the middle point protection. So what is the middle point protection? The concept of this is very simple. The middle point protection is, let me look at this. The middle point protection means if P1 find out I cannot go into P2, P2 got a problem, this place got a problem, then P1 will directly will pass this. It will not send into it will directly send into the next segment, which means P1 knows the P2 got problem. So I will not send into 3::3. It will directly send into 06::6. It will directly send into here. It's called middle protection. It will isolate this. How do I say? Isolate this problem point to isolate it. Okay. So this is a middle point, and this is how we do the implementation. So basically, we can say the P1 knows that there is a problem for this 03 got a problem, so it will become 04::06:6. And here, here sometimes the devices will do additional behavior is if the SL is become 0, they actually will put how do I say this? They will put an outside channel. they will do the TRFA again in case there's some micro loop situation happening. So they will do the TRFA calculation again and put the outside SRH and help me sending to the destination. Okay, but this is not always happening. This is because my SL segment left is equal to 0. They have the chance to occur the micro loop. Then during that time, they will do the TRFA calculation again to add some SRH. But if the SL this here is not 1, I will not do the TRFA. Okay, it just in special circumstance they will do it like this. Okay, so let's continue. Okay, so that is the middle point protection. Then let's look at the macro loop introduction, like why. Yesterday we also talked about the macro loop, but not too much detail. But here let's jump into detail. So first, why macro loop is going to happen? We know the TRFA FR is okay. They already can prevent the macro loop happen, but why we still need the macro loop protection? Okay, it looks like this way. First, I have primary path, and this path is, if it is got filled, I will go to the FR path. The FR path will add an additional SRH header into the devices. So during this time, since I have the SRH based on the TRFA, there's no loop, there's no micro loop, but eventually there will be some backup path. That backup path maybe will be converged. And after that, I will not go into the FR path anymore. I will go into that real backup path. I mean, post-convergence primary path. I will go into here. So during that time, if the backup path, the post-convergence primary path is converged, I mean, then they will not do in FR way, which means they will not add the SRH header into it. So during this time, they might be micro loop happen. Let's look at the left, right picture. So for example, P1 completes the IGP convergence and does not forwarding the traffic based on the FR because P1 is finished the convergence. P1 do not need to forwarding the packet based on FR anymore. So the P1 will sending the packet to the P2 because at the very beginning, the P1 knows the P1 and P4, this link is filled. So P1 at the very beginning, it will just based on the tunnel, based on the FR to forwarding the packet. During that time, there are no problem. Then the T1 finished the convergence. It was thinking, okay, now I will finish the convergence. I do not need add additional SRH header. I just follow in the normal way. So it's sending to P2. But P2 during this time is still thinking, if I want to go into the PE2, I should sending in this way. So here it will create a macro loop. So how to protect these things? First, macro loop have many different type of macro loop. Let's look at the local macro loop in a traffic switchover scenario. Okay. So this this kind of loop is what we just said, that the P1 is finish the IGP convergence and do not forwarding the traffic based on FR. Sending to P2, P2 do not finish the convergence, so it was sending back to P1. You can see because this cost is very large, P1 going to P2, still going to this way. So this is the first type of macro loop. This is a traffic switchover scenario. Okay, so to protect that, we just need some symbol, some very just one command line, it will be okay. But about the command line, later, you can check the documentation. Okay, about the command line, it is very easy. I will not say it here, but let me tell the how is this working? Like how is local macro loop avoidance help us to bypass it, help us to avoid this situation. So for this one, the working principle, how to solve it, it is very simple. P1, after they finish the convergency, they will not directly quit the TR-alpha status. They will wait a time until the time expired, which means until the P2 finish the convergency. Then the P1 will forwarding the packet in the normal way. Okay, so this is for the local macro loop avoidance. Okay, and here is something else called remote macro loop. And the remote macro loop is working like this way. First, the P1, the P2, sorry. First, P3 and P4 got a problem. There is got a problem, and P2 finished the convergency. P2 knows that this path is not okay. It is disconnected. So the P2 will send into the P1 and send here. But during this time, P1 do not finish convergency. The P1 thinking, I should go into P2, I should still go in this way. Then it will create a macro loop. It will create a macro loop. So to solve this problem is also simple. So basically, we will in the P2, sorry, when the P2 sending the packet to the P2, sending to its destination, P2 will also use the TR-RFA to add some SRh header to create some explicit path to its destination. So for this, there will be no problem. There will be no remote macro loop problem. Basically, just in P2, we enable some feature, it will be okay. It will be just okay. So there will be two ways, strictly explicitly or loose path. They basically, this is a hop by hop, and this only ask the P1 to forward in some special link, it will be okay. Okay, so this is a remote macro loop avoidance. And also there will be some macro loop in a switching back scenario. Okay, so the situation is like this. Assume that the link between P1 and P4 here is recovered. The link is recovered, and the path from P1 to P2 will be P1, P1, P2, P3, P4, P2. This is the traditional one. Then this is recovered, and then the P2 first they finish the recover. The P2 knows, okay, this is recovered. I should sending back to here, but the P1 is not finished the recover. So I will send into P2. So it will occur the loop. To avoid this, also same thing. I mean, use the TR-RFA FR for P2, create some explicit path, use the SRh, and fourthly, forwarding the traffic from P2 to P4 to P2. It will be okay. This is how you avoid the macro loop, like in a traffic switching back scenario. Okay. Okay, so this is a local protection technology. Any question? Okay. Then let's continue to talk about the end-to-end protection technology. The end-to-end protection technology first is HSB, hot standby. So basically, you just create two candidate paths. One has a higher preference, and another has a low preference, and this one will be active. And if this got a problem, for example, some link is failed or something, then I will switch over to here. Okay. Another is the ECMP. We can, in the same candidate path, we can put two segment lists, two paths. One path is here, another path is here. And if this path is failed, this path failed, I can go this path. Okay. Then another is best effort. The best effort is you can consider it is an escape path. It is an escape path that in case your primary path and your backup path is all failed, all your candidate paths cannot work, then you can use this best effort path. As long as the P1 can reach to P3, no matter which path they are, no matter like which link they're gonna pass this traffic, gonna pass which link, I don't care. As long as the P1 can reach to P3, it will be okay. Then P1 will reach to the destination. But maybe they are not following the how do I say the planned path. They are not following that, but they can reach to the destination. So this is third way for end-to-end protection. Okay, any question? Okay, so let's continue. Let's say the egress protection and access protection. Okay, so for the egress protection, it means that for this link, for this link got problem, we can use like a local protection, no problem. And for the other things like end-to-end also is okay. For example, this link is not good, I can use end-to-end link. But what if the endpoint got a problem? What if endpoint got a problem? This will, because for a tunnel, this must have a source, must have a destination. But what is the destination got a problem? This tunnel got nowhere to go. So here is the egress protection gonna work. So in the most of the time, even in the real network, for the most of the time, we will use the VPN-FR to help us to do it. So VPN-FR very simple. You can say C2 and P2, they all receive the network from CE2, the network 2 from CE2. And the P3 was sending the route entrant, P2 was sending the route entrant. The next hop will be different. And for the PE1, they will use the P2 as a primary and the P3 as a backup. Okay, then if the P2 got a problem, I will use P3, VPN-FR. This is a widely used but also a very simple way to how do I say this? To guarantee, to prevent the egress failure. And besides this, this is the most commonly used. And besides this, we actually have two other technology. One is called Anycast FR. Anycast FR, we can put two egress route within the same locator. So if one egress is failed, I can go to another egress. Okay. So this is endpoint, the egress device, and let's look at the access protection. Access protection. Access means here and here. So let's look at one protection called the mixed VPN protection. The mixed VPN protection. The mixed VPN protection is working like this way. The PE2 to CE2, they are going with the normal link with a native IP link. And from PE2, there will be another path. Is from PE2 to PE3. Here they will use the SRv6 tunnel from PE2 to PE3. And from PE3 to CE2, it will be the normal native IP link. So you can see the backup will be this, and the primary will be this. They are mixed. So this is some way for the access protection. Okay, so this is all for the basic idea for SRv6, the working principle for the SRv6. Any question so far? Okay, if there's no question, let's look at the configuration. Oh, okay, let's look at the configuration quickly. Okay, so this is for the SRv6B to carry the level 3 VPN v4. Very simple. Just this is for the VPN v4 exchanging the peer, exchanging the BGP peer. So enable the SRv6 encapsulation source is here. Locator, set a locator, and use this source address. Use this where the source? Use this source address and this source address to create the VPN v4 peers. And for ISS1, we also need to configure the segment, because we need to ask the ISS to forwarding the locator, right? So, and also P1, you create the VPN create a VPN here, set the RD, RT. Then using the segment routing is the best effort. Use the BE to do it. Because this is another peer, so establish the BGP peer with it. And segment routing locator will be AS100, and it will be okay. And the P2 doing the same configuration. Then you can do the ping. So for the policy, similar. So for the policy, we need to do the first. We also need to set the VPN v4 neighbor, setting VPN v4 neighbor, and setting the locator at the PE. Set a locator, set the OP code, set the source address, and then in PE1, establish the neighbor with PE2, establish a neighbor with PE2, and use ISS to advise the locator. And you can set the path, the segment list. This is the path. Indicates 5 is seed IPv6, which means this device, and then the next hop will be 33, which means this device. And then create some SRv6 policy. The policy is named 1, endpoint is 3::3 is this device, color is 101. You can set the binding seed if you want, and also set this candidate, create a candidate path, preference will be 100, and put this segment list into this candidate path. Then you set the VPN instance, create some like set this VPN instance is that use the traffic engineering. And if you followed with best effort, it means if this T is filled, I can use BE as an escape path. Set a locator. And PE2, when it forwarding the or receiving the route entry, we need to add the color. So here is the import route policy. But if you also can configure at PE2 when it's sending to the PE1, configure the color. Okay. Then the PE1, we need to create some tunnel policy. This is how you select the tunnel. We selected the SRv6. So the tunnel policy we used in the IP VPN instance. So which means this VPN instance when it forwarding the packet, it will try to find the SRv6 tunnel and use SRv6 tunnel to carry the traffic. Okay, then and this is how you verify. And we will do the ping. About detail, we actually later we will do the demonstration, about it. Okay, and the last we will talk about the SRv6 deployment using iMaster NCEIP. So for to make this happen, we must setting some protocol, basically the BGP LS, SR policy, and the netconf. So let's look at how is iMaster NCEIP deploys SR policy. So first, we need to collect the network topology. We use the BGP LS to tell the NCEIP like what is my topology looks like, etc. Those kind of things. Then our network manager will input a requirement like from P1 to P4, the path should be this way. Then the NCE will calculate the path. It will calculate the path and sending the path based on the SRv6 policy, sending the segment list to the P1, and the P1 sending packet will following this path. So this is the key information required for the SRv6 policy path computation if you want to compute by the NCEIP. So this is the information that needed to be collected. And this is how we do the configuration. If we wanted to collect all those information, we need to use the RSS to do the configuration. This is if you wanted to connect with the NCEIP, right? This is what kind of configuration you need to configure. But if we just doing the how do I say, doing the static way manually to configure the SR policy, a lot of configuration is no need. Okay, this is most of the time, especially for this part, most of the time it's just for NCEIP, because I wanted to let the NCEIP know my situation, know my topology. Okay, now let's continue. And this information, it will become, it will send into the BGP LS, and the BGP LS, it will reporting to the controller. Okay, then for the BGP LS, if we wanted to deploy the BGP LS, there will be two ways to establish the neighbor relationship with NC-IP. First, each device can directly establish the BGP-LS relationship with NC-IP. Another way is we send into the RR and RR connect with NC-IP. This one is better. This one is better. Okay, so this is how you do the configuration. You can check. This is at this P1, this device is how you do the configuration. And this is where in the controller where you do the configuration. Okay. And after we establish the connection for the BGP-LS, then we will collect all kinds of information we want. So then we can do the calculation based on the minimum cost, the minimum delay, bandwidth balance, etc. And we can say this is the result after we do the calculation. And we can just click apply, and this path will forward it to the source point of the head end. Okay. So for the SR policy, if we want to deploy this, we must configure the SR policy. So SR policy, we also have multiple ways. First, for SR policy, only the edge devices PE2 is needed to establish the SR policy. So there also will be many ways, but recommended is you are creating the SR policy with RR, and RR establish the SR policy with NC-IP. This is still recommended. Okay, here is a configuration. Okay, so this is for the VPN. Then we can create some certain VPN in the controller and binding this VPN with use the tunnel policy to binding with the SRv6 policy or SRv6 policy group. Then and based on the color, we can do the forwarding. Okay. So about the NC-IP controller, we will not talking too much. We just briefly mention about it because in our lab demonstration later, including the lab guide inside the lab guide, we will not talking too much about the NC-IP. Okay, just you got an idea will be okay. Okay, so for the rest, there will be no further information. Okay, so this is for the SRv6 fundamental and the configuration. Any question for this? Okay, no question. Okay, if there's no question, I guess let's take a short break. Then later we will start the lab demonstration. Okay, let's take a 15 minutes break, and after that we will start the demonstration. I will show you how to do manually to create the SR MPLS policy and SRv6 policy. Okay, so let's take a short break, and later we will start the demonstration for the lab.